Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. In our previous class, we were talking about the development of finite element equations for one-dimensional axial bar problem. This is what we did. We did halfway, and let's continue it. Just to recall what we have done last time is that there is the governing equation d dx of AE du by dx plus q is equal to 0. Q is the distributed load along the rod, so which we converted to the weighted residual statement briefly. So we multiplied with Wi, and we also added these boundary terms because there is a force being added. So that force is given by AE du by dx at x is equal to L is equal to P, and which we write here as a residual term Wi prime. And as usual, so if you do the integration by parts, so we get the first term as Wi AE du by dx at 0 to L, and the second term is minus dwi dx AE du by dx, and one more term Wiq, and then there is a bounded term. So what we did is that the advantage of this weak form is to cancel. So this at x is equal to L, Wi prime AE du by dx will be cancelled with Wi AE du by dx by choosing Wi prime is equal to minus W, and the one of the bounded terms at x is equal to L gets cancelled, still leaving the lower term Wi AE du by x is equal to 0, and the other terms as well. And this obviously we know that will be made to 0 by choosing Wi is equal to 0. So that means that the weighting functions which you have to choose should be such that they are 0 at x is equal to 0. So if that is the case, then the final equations which we get finally what we get is dwi by dx this is equal to okay. So this is the weak form of our weighted residual thing, and then where the u hat is the approximation which we do piecewise approximation. So this is u hat x is doing piecewise approximation. So what we have here is as usual so that means that so we have as we have discussed this a number of times. So this u e it should be such that it should be non-zero within the element, and it may have discontinuities at the element boundaries, but the discontinuity is limited to a finite discontinuity, which means that u e or u hat should be a C naught continuous in which case, so we did this as Ij for any general element. We did this so this is for a general element. This is how it looks like. So that means that this weighted statement will be this is odd number of elements. Okay, so this looks thing, and so in particular, this can be written as Kij Uj no, this is not integral. So this is also not summation. Okay, they are not summations, so it is simply this kind of thing. So we know that this ith equation is looking like this one, right? And so this is essentially assembled. Okay, so this is where Kij is a general term. So for element so this we have seen. Okay, in our earlier heat conduction problems and all that, this we have seen. And then this Ke here is simply belonging to I and J okay. So for we know that Ni is Xj minus X divided by H, X minus Xi by H. So this is how the shape functions are, right? Okay, so this is all our usual procedure. And so coming to this here, so Kij, so this, if you simplify a little bit, So Kij for the element. So taking Wi to be obviously Ni. So this is nothing but dni by dx. Okay, so this is what we did. And this is over the element. And this becomes a general I and j. So this is a general ij. Let us say ki when we take both ij and I and j to be equal to I. So this will be dni by dx. So this is minus 1 by h ae minus 1 by h. This is what the derivative is. So this will turn out to be 1 by h square and another h there is coming. So it is essentially E by h. Okay. So like this we can derive other Kij and Kji and Kjj. So exactly the same procedure. So this is the element contribution. And so Kij of the element is similarly dni by dx ae okay. So this will turn out to be minus 1 by h, okay, for the jth thing. And this is 1 by h. Okay, this will be simply as such. It is minus ae by h. And so similarly, kji, we know that it is the same as kij because these ni and nj gets interchanged. And that's all, minus ae by h. Here, of course, one thing which we are assuming that a is here, a is a constant. So here we are assuming that a is equal to constant. But otherwise, if a is a function of x, so you have to integrate it as while doing this evaluation. Okay, and similarly, kjj is simply dnj by dx times ae dnj by dx. And this is simply 1 by h ae 1 by h dx. Okay, this will turn out to be simply again ae by h. So thus these four terms can be put into this K matrix as ae by h 1 minus 1. So another interesting thing is that now I said that a is equal to constant, but a can be a different value for different elements, and you can take it to be the average value in that element. And similarly, it is true for E. So this is the for, so that means that this has to go to I and J. So it goes to Ij, whatever be Ij. There is one more term that is left, is the boundary term, so which is F or B if you call it. So the load contribution, here we can say the right side vector we can say as Fi is nothing but Ni q bar dx. So this is a load distributed over the element, and also Ni times P at x is equal to L. So this is what we have here. And then this is Ni q bar. Let's just see, we need not do it again and again. This is Ni and this is okay. So if you think that the load over the element q bar, distributed load, is constant, so if q bar is constant, then Fi will be just integral of this one. So without doing too much of integration, so the Ni value is equal to 1 here, and then it linearly goes to 0 here. And so its integral is simply, if this is h, the integral is h by 2. Right? So the integral of Ni, which is a linear function like this one. So, okay. So similarly, we can also do Fg right away here. So it is q bar and j dx. So similarly, I'm writing it here. So we have, this is again q bar h by 2, because this is the linear thing and this one here. So that way the force function on this one is nothing but q bar h by 2, right? And then there is one more term here, that is this Ni times P evaluated at x is equal to L. So this Ni, as you know, that over the number of elements here, if you just recall. So here for the contribution of Ni times P at x is equal to L. So if you see that there are a number of elements here, and so you can very well see that Ni, if you just take this element Ij, so this element is 0 only over this element omega e, and turns out to be 0 here and 0 here, right? So if that is the case, so that means that for interior elements, so the contribution here is 0, but however this will be the, so this contribution is 0. This is also what we discussed yesterday in the case of heat convection problems in 2D. So the same thing is true for any similar applications. For interior elements, but for element on the boundary, so you can even say for the last element on the boundary, so this NIP at x is equal to L will become Ni will become 1 there, and it is simply P. Okay, I hope you have understood. So that means that this contribution should be non-zero, will be non-zero only for the last element, for the last node. Otherwise, its contribution is 0. Okay, so this is how we evaluate 1D solid axial rod problem with the distributed load and the end load. Okay, so we did it for one element, that's all. So for a number of elements, if you have more and more number of elements to increase the accuracy, so this element need to be, so if you have a number of elements here, 1, 2, 3, 4, 5, 6, and so on. So what you need is that you have a system matrix here, global matrix, consisting of, say here, Q7, so this is the global matrix, right? And then this Kij will go to any place. Okay, so this is how the assembly has to be done, and you can apply the boundary conditions. Okay, so you have to choose appropriately those equations, and those equations which have been obtained in a consistent manner from the point of view of the weak form, in the sense that, so here if you think that this node number 1 has 0 boundary condition, 0 displacement, then what happens is that the weighting function or the shape function which you can choose should be equal to 1, a 0 there. So that means that the first equation which have been obtained obviously is taking Wi is equal to N1, and that is not a valid equation, and that means that it is it cannot be considered for the solution purpose. So that means that the first equation should be ignored, and the other, say here, other 6 equations can be used to find out the 6 unknowns U2 to 7. Okay, here in this. So the examples which you take, you should keep this in mind, and then you should solve for the global equation, for the global solution. Okay, we will do a 2-dimensional numerical example a little later, but the procedure is all the same. So now what we do here is that let's go to 2-dimensional problems. So that is quite important, and which will be extended to 3 dimensions very easily. So let's do finite element equations for for 2D solid mechanics. So 2D solid mechanics will be a problem in XY axis, right? So this can be a thin plate which comes under the plane stress assumption, or it can be a very long dimensioned in the z direction, very long extruded kind of cross section. So in which case then it will be a plane strain problem. So in either case, so the approach, the equations are all same except the constitutive equation. So let's just so the here for any point P here, so U so we will deal with problems with both the problems, either the plane stress or plane strain together, right? So here this is the basic primary variables. So this is the displacement. So the governing equations are governing differential equation or in terms of stresses. So these are the two equations. So these are the two governing equations. Okay, and also we have the constitutive equations. So we will simply write it as a D matrix here. Okay. So this can be either plane stress or plane strain. Okay. So this is the basic governing equations. So let us try to formulate the residual statement. So what we are doing is the method of weighted residuals. So the same solid mechanics problem can also be handled through the procedure of variational approach. Okay. And also there is a third approach, which is the virtual work principle. We will take it up. The first will take up the method of weighted residuals. And this method of weighted residuals is, of course, Galeckin approach, where the weighting functions are the same as the trial functions, whereas variational approach is altogether different. So where we formulate the functional and then we'll try to either maximize or minimize that to obtain the solution. Okay, in the method of weighted, so you can even say that this is the first approach, and we will take up the variational approach after this, and we will indicate this approach again from the point of view of the virtual work little later. So this method of weighted residuals approach is most general in the sense that whenever the equations are given in this form, either one equation or two equations, or even sometimes three equations, so the procedure is same. So what we would do is that we will formulate the weighted residual and then get the weak form, and then we will do the approximation for each variable. Okay, now let us see how we do it. So these governing equations are in terms of places. Okay, let's just do method. So there are two equations here. So the first equation, so it looks like this one, Wi. So this is residual, and we will integrate it over the whole domain omega. And then we also have the weighted residual because of the traction boundary conditions here. So there is a traction boundary conditions here, gamma t. So the traction boundary condition, let me write it here. The boundary conditions are, I already mentioned it earlier. So it is nx tau xy by ny is dx, and tau xy nx as you know, the nx and ny are directional cosines of the normal on the boundary where this traction boundary condition is prescribed. Of course, there is a displacement boundary condition. So this displacement boundary condition we will apply as such, because that's not very difficult. So that need not go into this. So let's write this one. So Wi prime. So this is an integral over gamma q and sigma x nx tau xy and y minus t bar x over gamma. This is equal to 0, right? So let me just stop it here, and we'll continue this in the next lecture. Okay, bye.